Welcome back to this afternoon's Symposium on Bio-Cybersecurity. I'd like to now introduce our second session entitled, What are Bio-Cybersecurity Threats? We will again hear brief commentaries from our three panelists, followed by a moderated discussion on bio-cybersecurity issues, such as DNA synthesis and biomanufacturing. A friendly reminder to utilize the Q&A function to ask questions of our panels. These questions go directly to our moderators, and we again encourage your participation in today's discussion. Our moderator for today's second session is Rebecca Moritz, Biosafety Director at Colorado State University. And I'll now turn the session over to Ms. Moritz to introduce our panelists as they provide their brief remarks.
Thank you, Meg. Our first speaker in this session is Dr. Jean Piccoud. He is a professor in the Department of Chemical and Biological Engineering and the Abel Endowed Chair in Synthetic Energy here at Colorado State University. Dr. Piccoud.
Hold on. I'm coming. Sorry. So thank you very much for the invitation. I'm very grateful to be here today. And I would like to take advantage of this opportunity to start a conversation about the way we screen DNA sequences for biological risks. Let's start with the basics and what is biosecurity. So if you Google biosecurity, you will end up with a number of links to pages describing policies to protect agriculture from various diseases. And the bigger brigade, is in charge of preventing pests from entering the country at the airports. We've all seen them. So fundamentally, biosecurity is about preventing a biological threat from entering a community. Well, that was at least what biosecurity was until 2005. In 2005, scientists at the CDC used chemical DNA synthesis to resurrect the strain of influenza that was responsible for the 1918 Spanish flu pandemic. This pandemic killed over 35 million people worldwide in less than 2 years, so it was the most devastating pandemic since the Black Death. And that strain of influenza was not present on Earth anymore. There were some relics of those sequences in corpses that were buried in the permafrost in Alaska. And so people could sequence it and reconstruct the virus. And obviously, this was a very controversial research project because what if, even though there was a legitimate reason to do it, there was also a risk of a leak in the environment or people using the sequence for, I was told that people don't see my sequences. I apologize for that. Can you see my screen? Can somebody see?
No, we can't.
Oh.
John, would you like me to show your slides?
Give me another chance.
Okay.
Do you see a screen now?
No, we don't.
And now?
Yes, we're getting started.
Okay.
But not the slides yet.
No, you don't see the slide. Okay, sorry. Apologize. Hold on.
Okay.
You see the slide?
Yes.
Okay. So I apologize for that. So I lost my momentum. Yeah, so they were able to, that was somewhat of a controversial project that represented a certain biological risk. And that got people attention. So quickly after that, there was a English newspaper that published a story explaining how easy it was to get DNA fragments containing, a small part of the smallpox virus genome. And so now we are in a situation where our understanding of biosecurity is changing, because the threat doesn't need to come from the outside. It can come essentially from inside, essentially through a computer network, just through access to information. And the threat may not necessarily look like something that is outside of our community. And so this kind of attention was not good for the gene synthesis industry. That industry was just pretty much starting at the time. So they very rapidly organized themselves and develop a protocol to screen their orders to detect the presence of suspicious sequences. Today, most of the gene synthesis companies and the number of biotech companies that are not within the gene synthesis business, interestingly, are members of the International Gene Synthesis Consortium. And you can go on their website where they publish their harmonized screening protocol. At the same time, the government also paid attention, and they developed a document describing their recommendation about the screening of synthetic DNA orders. A draft was published in 2009, and a year later, the final guidance was published in 2010. It includes multiple sections such as customer screening, record retention, relation with the government. But the sequence screening was the one that we particularly pay attention to. And this document is actually fairly similar to the one that was proposed by the industry. So that's good. The goal of the sequence screening is essentially to detect sequences that may be embedded in gene synthesis orders that are specific of select agents and toxins. So select agents and toxins, that's a list of infectious agents that have been put together by the government that are particularly dangerous. And so it includes both DNA sequences, but also protein sequences. And they are looking for sequences that are only found in select agents and can be as small as a 200 base pair. So essentially the screen goes like this, it performs a 6-frame translation of the DNA sequence. The DNA sequence is broken down into smaller fragments of 200 base pair. Amino acids, the proteins are broken down into short blocks of 66 amino acid sequence. And then you use, sequence alignment tools to compare those fragments to gene bank entries, and you look at the keywords associated with the annotations of the base hits. Then you analyze these keywords to potentially flag a sequence. So during the summer of 2010, I put together a team of students to do what I think was the first implementation of this guidance, actually, and to evaluate its performance, because it was not totally obvious to me what kind of results we would have when we implemented that screen just from the text that was in the Federal Register. So the good news is that on one hand, it worked. It's able to detect small fragments. The computational cost was acceptable, and it was relatively easy to implement. Didn't require, an extensive curation effort of sequences. But on the other hand, there was a lot of interpretation that was necessary to do the implementation. There was no target accuracy for the screen. There was no way of knowing whether an implementation met the government expectations or not. And then we found also some major vulnerabilities in the way the screen was designed. So at the end of the day, you end up in a situation where different implementations of the same guidance could lead to completely different screening outcomes. And that's probably a little bit of a problem. We published that paper, those results in Nature Biotechnology, released the software open source. The students were part of iGEM, so they went to iGEM. At the time, security at iGEM was probably not the most interesting projects that you could, present. So the reception was a little bit lukewarm. I think that it has gone better, especially, due to the outreach that the FBI has done over there. So, I think that the iGEM community is much more aware of security now than they were 10 years ago. But the interesting part was that the day after the iGEM Jamboree, the students were invited to present their results to the government. And so they gave 2-hour lectures to 30 people representing, I think, something like, 15 different government agencies. And there was much more interest from the government than actually from the iGEM crowd about those results. So the experience of implementing the guidance and seeing the reaction that we get after the work was published makes me think that maybe we've not been thinking about this in the right way. I think that there's a number of problems with the way the screen is performed today. First, the focus is way too narrow in terms of both, what are the sequences that we are screening and what kind of threats we are looking for. Also, somehow the gene synthesis industry has been tasked with performing those screens, but it's not their job. Their job is to make DNA, not to do biosecurity screens. And for them, it's just a cost that eats on their bottom line. So they have actually a financial incentive to limit that expense as much as possible. Also, the malicious use of gene synthesis seems a fairly hypothetical threat at this time. And there are a lot of people who have been asked to do that, who essentially tell you, why would I spend so much effort into detecting something that I will never see in my lifetime? So I think that, there are a number of problems with the way we've been doing it, and there is a renewed interest for this. And so maybe it's a way, it's time to be changing slightly the way we're thinking about it and broadening our perspective. So one way of broadening the perspective is to broaden the scope of what we are looking for. And in other areas of security, combination of things that are not dangerous on their own can be strong signals that something bad is about to happen. And so it really doesn't take a whole lot of imagination to come up with dangerous combination of DNA sequences. And I would invite you to, to do that exercise, spend 15 minutes, think about it. And I bet that you will come up with half a dozen strategies that would not require major equipment or special skills. And that may be very, unfortunate combination of sequences that are not dangerous on their own. The other category of sequences that we should be concerned about are the ones that don't match any natural sequences. And this is a plasmid that was designed in my group. And the sequence in blue, it's about 3 kilobases of DNA that was generated by a computer software. And when you run that against gene banks, you don't get a single hit. And I think that, this sequence would go through the current screening protocols very smoothly because it doesn't match any select agents. But I think we should be a little bit more concerned about 3 kilobases of DNA sequence that we know nothing about, that 200 base pair of any viral genome. Finally, I think that we need to put the screen in context. Some sequences that are not dangerous in the hands of qualified scientists could become dangerous in the hands of in the wrong hands. And for instance, if you take adenovirus, which is used in a number of clinical applications, it's safe, it's not on the select agent list. And that sequence coming from a pharma company would not raise any questions because, they make a lot of products that use that. However, the same sequence coming from a community biolab would probably deserve a little bit more investigation because, do-it-yourself gene therapy or gene editing projects is probably something that we should be aware of and want to oversee in some way. So in a previous life, I used to do a lot of professional flying. And when you fly an airplane, maintaining situational awareness is key to safety. And situational awareness is actually a model that can be applied to a number of different security and safety scenarios. And essentially, it says that decisions should be taken based on a number of environmental signals that are integrated to get a picture of the current situation and try to interpret where the current situation is going to lead you in the future. So we could apply this model to sequence screening. The signals that we could get are more than just synthetic gene orders. It's just one signal. Design files on the design files that are on our computers is another signals, our oligo orders, or even the DNA sequences that are produced by our DNA sequencers are other signals. The comprehension is really about the bioinformatics analysis of those signals to produce some information that is understandable by a human operator without a PhD in bioinformatics. I think that the projection now consists in connecting the results with people associated with these signals. No sequence is dangerous on its own. It's only dangerous in the hands of someone. And so the question is, are the sequences aligned with the activities that the people have disclosed or been approved to do. And if there is a discrepancy between the sequences that they are working with and what we think that they are doing, then this is a red flag that requires some investigation and some action. And the action is not necessarily, oh, you shouldn't be doing it. The action may be, well, we need to update the scope of the approvals or the, of what you've been doing because, we miss some information, or maybe you want to rethink that project of that order and do something else with your time and your way. So it seems that the purpose of sequence screening doesn't need to be limited to looking for a bad guy trying to use gene synthesis for malicious intent. And it's actually fairly well aligned with the standard biosafety policies and practices that we already try to abide with. And we actually have a great biosafety system in this country. I don't think that biosafety incidents need to be reported. And I spent some time trying to find statistics about biosafety incidents. I didn't find any except, anecdotal evidence that the track record is actually pretty good. Number of laboratory-acquired infections is very small and things like this. And it's somewhat similar to the outstanding safety record of the air transportation system. And I think that when you put the two side by side, there are striking similarities in the way they are organized, except for one thing, that the biosafety world doesn't have any technology. We don't have any software. We don't have any biosafety technology system that really makes it possible to implement a lot of the policies and the training and things like this. But I don't think there is any reason it could not be developed. And I would be very interested in talking to anyone who might be interested in trying to figure out what this may look like. So I'd like to acknowledge the students who were part of the 2010 iGEM team. It's interesting that a lot of them did very well and have become data scientists over the years. And I would also like to acknowledge the people who sponsored that project. I'm going to stop sharing my screen.
Thank you, Jean. Our second speaker in this session is going to be Wayne Osteed. Wayne is the Chief Technology Officer at the National and Homeland Security at the Idaho National Laboratory. He is also the Chief R&D Officer at Cyman 2 Manufacturing Innovation Institute. Wayne?
Okay, can you see my slides? Let me put them in presentation mode here.
Yes, we can.
Okay, thanks for the introduction. I'm going to step back a little bit and talk about some of the strategic cybersecurity threats to manufacturing in general. There's many sectors, manufacturing and otherwise, that can show as examples for what we're going to face with these strategic threats so that you can try to translate them to some of the unique systems and unique consequences that we're going to find in the bio-cybersecurity arena. And I think that Charles may touch on some things relating back to those areas. So first off, Cymani, the Cyber Manufacturing Innovation Institute, is one of the half a dozen and a half manufacturing innovation institutes across the nation. Dr. Lee is from another one, Nimble, which is dedicated to the future of biomanufacturing. This one's one of the newer institutes dedicated towards cybersecurity manufacturing across all sectors, initially funded by Department of Energy and various matching funds on sectors of interest to not just future jobs, but also a global impact in terms of energy and emissions efficiency. And that's a very dominant DOE theme. However, there are some more recent engagements with partnerships with Charles, with National Resilience and Nimble itself, where we hope to use some of the things that we're developing and learning and over time to be able to apply and extend into the biomanufacturing sector, which is unique and will require its own innovations. There are significant assets to be brought to bear. And since manufacturing is a inherently cross-pollinated sector, some of the things, particularly on transportation and delivery, are intertwined with the delivery of the production of different biopharma outputs. So the manufacturing sector, when you look at the biggest sectors are getting attacked after financial theft, if you will, from banks and credit card, but the actual control systems and delivery sectors of various physical functions, the power grid and manufacturing sector are always some of the top ones. And one of the long-term challenges that we have is that this sector and IT sectors in general have been driven by a push to market of technologies as opposed to a secure to market of technologies. And that has some aggregated risks in the end. If you look at the costs in order to fix software flaws, cybersecurity or otherwise, as it's pushed towards closer to the end user or to the end nation, it really escalates in terms of orders of magnitude of what it takes to solve this problem after the fact. And unfortunately, we are where we are, but we still have to address some of those fundamentals and do it in a way in which it's pervasive, unobtrusive, resilient, and economical, so that it's almost transparent to the small innovator that he's joining this ecosystem that has some assurances that are validated at scale in order to participate in this ecosystem. So that's the long-term challenge that research institutes are dedicated towards. And this is the framing, if you will, relative to this institute and the cybersecurity challenges. So let's step back and look at, in this example, how the complexity and sophistication of attacks has progressed in control systems, taking sort of the power grid as an example. The well-known attacks in winter of 2015 on Ukraine by Russian elements, in which hundreds of different substations were taken down and were down for many days, servicing many different customers. This attack was very manual. There was a lot of targeting that went into getting into these systems in advance, but once they're there, they actually use the systems and the human interfaces against them and use them almost as designed, but taking control as the operators in order to do these outages manually. And there's a large number of coordinated teams that did this. One of the things that they did do was a sort of a scorched earth policy afterwards, in which they bricked, if you will, the communications devices that were doing serial to fiber conversion. And so they lost ability to automatically control many of those substations and had to operate them manually for, in this case, years, because they were not able to replace those automation systems. There's many power grids, including our own, many sections of it, where it's not possible for us to wield that type of power in a manual fashion, given the margins that we're running. Part of that attack, first attack, they sucked up a lot of information about the configurations on the protective relays. And so they ended up gathering the intellectual property, if you will, on the safety systems unique to that grid, that was then also used in a larger attack in terms of megawatts, in terms of the transmission system that was hit the following winter. Now, in this case, this was a shorter outage, just a few hours, and not so ironically, it was balanced to trip a large amount of transmission, but not enough in order to scram most of the power reactors that would have to gone offline if they took off enormous capacities of transmission. So they did not go into multiple days or weeks worth of outages because the reactors would have had to been then restart in a very slow process. So very targeted in a physical sense of the type of effect they wanted to have without going beyond it. This one was automated. This was not manual. And so as you see the progression of targeting information that you get from those scientific or engineering workstations, the next level was to the safety instrumentation systems, if you will, on a different type of attacks on Middle Eastern oil and gas processing facilities, petrochemical facilities. And these attacks were actually against the safety systems. So these were memory-based attacks in which they could load different software and change different settings. They're actually keeping the plant within safe control parameters. So in these type of plants, there are parallel control systems that are used, if you will, to implement the formula. If you're doing a chemical processing plant in order to produce it at scale, that, you know, that may be intellectual property in a sense, but these were the actual safety systems run in parallel to guarantee that there wasn't different safety events or explosion events should those processes that are being controlled by the production systems be upset. This is useful in an attack scenario if you are trying to disturb the process and not have the safety systems kick in and effectively take that plant out. Again, they hit the engineering workstations, a half a dozen of them. Even though there were some keys involved in whether or not you would load the software, so you kind of turn the key to load program versus run, that was marketed as a form of protection that was not necessarily in place. The fact that they were in the engineering workstations kind of makes that key sequence mute. As soon as they load new software, those engineering workstations are sort of key. And I think there's probably many analogies that you can take, although different systems as you go into different sectors. Some key takeaways besides the importance of these intellectual property stations being used to configure these systems is at the same time they had other objectives relative to influence and information war. But what you're seeing is a strategic targeting of diversity of systems as they progress capabilities and tested on real hardware. At the same time, in similar time frame, the US power grid was penetrated for over 3 years before they were detected, while information was being gathered about the various systems that we operate in, the different control systems that later have some similarities in some cases to where some of these attacks were taking place. So let's relate that now to what's going on in the last couple years. For all practical purposes, cyber attack in a criminal sense is commoditized. You don't have to develop the capability yourself. There's whole suites of services available to you in order to provide you the hacking hardware, the hacking infrastructure, the targeting infrastructure, even the monetization infrastructure, so that your targets can be dialed into, specified, developed against, using existing infrastructure and systems that have various forms of plausible deniability, and then how you monetize it in terms of ransomware and others. And so from a targeting standpoint, you could have some of these assets brought to bear against you, either because you look like a profitable sector because you're as a whole vulnerable, even if your individual facility is not of strategic interest, or you could be targeted in a sense that you are strategic to the US capability or strategic to our economic capability. And for those criminal elements cooperating with nation states, become part of the targeting system. The other thing to note is some recent supply chain attacks on software, hitting administrative software in the actual build process. These are fairly security adept vendors, if you will. I won't comment on the specific access vectors or their adeptness in this particular attack. But in general, these are experts in their field. And we're dealing with sectors that don't have these same level of capabilities at the same time as we have over 120 countries with various forms of different offensive capabilities under development. So when you turn to manufacturing, the simultaneous move of these digital threads, where we are linking the design cycle, whether it's a CNC machine with CAD software or biological protein printing machines with design software based off of DNA sequencing and trying to build the protein and lipid structures that you're looking for. This is happening at the same time as we're not necessarily coming up with a coherent architecture or security mechanisms or consistent protocols to address the fact that the database control is being exchanged, in a more worldwide orchestration of the supply chain, and we're dealing with, in many cases, older systems and a complexity of protocols. So part of the challenges that we're working on as an institute is that we have to move away from this patchwork of protocols and perimeter defenses and more to integrity checks and security properties that have the context of whatever physical, or in this case, biological process that we're dealing with, and enforce those security properties that we need to see across that digital thread between the design lifecycle, the manufacturing lifecycle, and the various analytic life cycles in terms of quality control, distribution, and links to other manufacturing systems. The final slide I'll have is a call to arms, if you will, from the Cyberspace Solarian Commission. And it effectively uses the words that I started out with, is that we now have enough aggregated risk in many of these sectors that has historically been pushed on to the individual company or the individual sector or the individual country that is not going to be tolerable for much longer. And so we have to move to a secure to market rather than first to market. And the only way to do that and preserve the agile innovation is to start putting these tools and thoughtful approaches and frameworks in place in advance so that the innovators are enabled with a DevSecOps or agile-like ecosystem that is relevant to their biosecurity or their specific manufacturing system. And so that kind of concludes my remarks, and I expect that Charles will close with some other more relevant biosecurity remarks.
Thank you, Wayne. Our last speaker in this session is Charles Froscia. He is the CEO of BioBright and the VP of Data and Dotmatics. Dotmatics. Charles, please go ahead.
Awesome, thank you. And Patty, would you mind bringing up the slides I sent you?
Absolutely.
So for anybody who doesn't know Wayne, Wayne is an absolute legend in this space, and I'm excited that he was able to talk with us today, because everything that Wayne talked about, the examples around the attacks on Ukrenergo, industrial control systems. Oh, we can see your messages just before you go any farther. The attacks on industrial control systems in the power grid and other sectors are unfortunately extremely relevant to our sector in the biological environment. If anybody is under the impression that biology is somehow immune to these kinds of high-end adversary attacks, let that end right now. That is unfortunately our future. Very near-term future is that we will probably get to see these kinds of attacks affect our workflows. That being said, I wanted to get to a little bit here through a few slides and talk about sort of digital biosecurity, cyber biosecurity, bio-cybersecurity. The field has come up with a lot of different terms, but we're all talking about the same thing, sort of the intersection of these two fields and the security impact on biological workflows. Next slide, please. Disclaimer, this is not meant to be a feel-good presentation. I apologize in advance. It is meant to be a call to arms. So if you heard it from Wayne, let me repeat it again. This is very much a call to arms. Every single person that is on this call, if I do my job in the next few minutes, you will either want to change jobs and work in this sector, or hopefully at least we'll get to think about it a lot more on a daily basis, because we need a lot more defenders and people thinking about how to secure this industry. We simply, as a nation and frankly as a species, don't really have much of a choice here. Next slide, please. So just a very quick sort of review. This is a selective sort of review of actions that have happened in the last couple of years ever since the pandemic hit. But just from left to right on the timeline, the Bureau, UK's NCSC, the NSA as well, DHS, CISA, a range of governmental actors have warned publicly that the COVID-19 crisis was a fuel for nation states and other actors to attack and try to subvert the US and other allies' response. So much so that the activity is extremely active. You have everything from disinformation and misinformation, which most people would know about around the vaccine, with the effect that we have seen in our country, as well as hosting malware on some of those sites. So they're not just doing single sort of attack vectors, they're doing multiple things at once. They're stealing information from regulators, like we saw with the EMA hack late last year, and then weaponized that information and re-released it to the public with the wrong information embedded in it. So what you need to understand very deeply is whatever we want to call it, bio-cybersecurity, cyber biosecurity, whatever the term, cybersecurity is now an integral part of biosecurity. We cannot have biosecurity without taking into account cybersecurity. It just isn't possible anymore. Next. Some of these examples were already brought up earlier and in the first panel, but the bottom line is that what we're seeing is that pretty much everybody under the sun is playing in this environment, and they're attacking, they're disrupting, they're stealing intellectual property, they're weaponizing information. It is unfortunately an extremely active environment. Next. 3, I'm here to tell you that virtually all of the tools, and this is why I wanted to follow Wayne and not be before him, is that all of the attacks that Wayne talked about, there are direct analogs in our field. And virtually all of the tools that are out there are insecure. Many of them come from an academic background where security is not the goal. The goal is innovation, and you want to move fast, right? The previous speaker spoke to that tension. But there's also a market tension, not just in the academic sense, but also in the environment, in the for-profit environment, where you're just first to market. Security doesn't matter. Instrument vendors haven't had to think about authentication and security and strong security built in from day one. This is not something you can slap on at the 11th hour. This is something you need to design in from the get-go. If you are in this sector, I urge you, please, please, please put this as a core requirement. We cannot build a secure bioeconomy and a bioeconomy that will even thrive if we do not consider security in the environment. And that could be biosecurity, but in particular, cybersecurity is an area that needs the most attention right now, the most urgent attention in my mind. So all of the tools that are in here, you have to think about everything from a plate reader to a bioreactor to a barcode reader. All of those are part of your critical path. And we need to secure them and to design them to have assurance built in. All right, next slide, please. This is a sort of the corollary of point 3 is that unfortunately, the vast majority of the world's biomanufacturing infrastructure is extremely vulnerable as it stands today. And I took an example. I wanted to bridge the two fields here. I took the headline from the Colonial Pipeline hack from a few months ago, if you recall, that affected the eastern seaboard here in our country, and just replaced a few words. This, of course, this is just, it's a play. It's a, you know, I'm making modifications on purpose here, but the reality is that a headline like this is probably not far from reality for us. And we need to start thinking about security, frankly, like yesterday, but you know, we need to really, really build this in. We cannot have assured biological processes without strong security built in at every link of the chain. Next. So, are you feeling bad at this point, or do you feel like completely lost and a little bit depressed? Next slide. Please don't. We really need you. It's time to get to work. It really is time to get to work. There's a ton of opportunity in this space. There's opportunity in the private sector, there's private in the public sector. It is time for us to get to work so that we can realize the explosive potential, in a good way, the explosive economic potential of the bioeconomy for our country. It is really time for you. This is I mean, I'm going to spend my entire career in this environment. Many of us in this room will, but if you're not considering it yet, please consider it now. Next slide. I'll give you a couple of examples. The company that I started and run, we did a joint event with Pacific Northwest National Laboratory. We did this at DEF CON this past summer. Tremendously successful event. We had more than 250 people sort of sign up with full names and resumes and everything, which is just phenomenal. People who really wanted to get into this event. And the goal here was really to teach them this intersection of the digital and the biological environment. How can you understand the threat space so that we can start plugging these holes? We need the workforce that will help us actually sustain the weight of this environment and start building a real foundation. Next. So here's what we need. We need defenders with an attacker's mindset. We need biologists and biomedical professionals. We need cybersecurity professionals. If there are any in the room that are interested, please come to Bio. We will cross-train you. We will help you cross-train so that we can actually build real strong foundations. We need people at this intersection. This is not going to happen if this community doesn't, multiply by 10 in the next couple of years. We will probably not be able to keep pace with the growth. Chemists, any scientist effectively that wants to learn about cybersecurity, that needs to learn about cybersecurity so that they can do their job better. Next. Here's what we must do. We have to learn from the mistakes and the history in industrial control system security. Again, Wayne is a leading light in that sector, and there are others at national laboratories and other environments, even in the private sector. We must learn from finance as well and the power grid. These are sectors that have gone through, and unfortunately, many of them we've seen recently have suffered through many of the same mistakes that we are recapitulating in bio. We need to build strong authentication, strong security as a foundation of our entire field. We need to build that from day one. We also need to assess the insecurity and security of the existing tools, right? If we don't know exactly what holes we need to go plug, well, we're not going to do a good job. And then finally, we really need to get together as a community. I have to commend the Alan and Ken here and the team at CSU for being clear leaders in this space. We need more of these. We need more of them around the country. We need more institutions caring about this and training people to do it. But I'm very grateful that we are able to gather here today. Next slide. On the community side, one thing I'll mention, Nina, who will be speaking in the next panel, who leads the Bio-ISAC, and I and others have come together to actually create an information sharing and analysis center. It is a nonprofit whose goal is to actually share information, threat information among industry members in private, so that we can actually, leverage the strength of the community and of the group, rather than sort of being isolated and getting picked off one by attackers. Our values there are very clearly rooted in helping securing the bioeconomy, helping sustain this growth for the long term, very action oriented, and really we aim to be a convening place for the industry. And so we would love to see any of you join us and sign up. It's a membership organization. Go online. Please sign up and send us notes there. We would love to have you. All right. With that, I'll conclude. Any questions for the panel?
Oh, thank you, Charles. Let's get Jean, Charles, and Wayne back together. We actually have numerous questions to kind of start talking through. I think the best place to start is we got a question from the audience. How is the average person likely to be affected by cybersecurity threat in the course of their daily lives? Who would like to take that one?
I can start. I'm assuming by cybersecurity you mean specifically in the biological space.
Yeah.
Is that?
Yeah.
Well, let's go back to NotPetya, right? Like is a good example. NotPetya was ostensibly a ransomware that hit many companies around the world, but including Merck. It led to, I think it was Kelvin that mentioned this particular example. It led to a $1.3 billion insurance claim, which ultimately was rejected. But more importantly, it actually led to a stockpile sort of loss at Gardasil, so much so that we had to go into the strategic national stockpile to be able to fulfill the need. So the bleak outlook is that you may not be able to get the medicine that you need. That's not speculation. We came pretty darn close with Gardasil. And it is in the public domain from folks from Bureau and others that nation state attackers are actively attacking the COVID-19 response, be it the cold chain, or be it instrument manufacturers, or be it stealing information. This unfortunately is very real, and the reality is that while it is not regarded as critical infrastructure yet, or is not recognized by the U.S. government as a critical infrastructure, being able to get my medicine when I need it is pretty critical to me and to everybody. So.
Would Wayne or Jean like to comment on that one? Otherwise, I got plenty of more questions.
I think Charles addressed. Let's move on through the questions so we have a diversity of
Sure.
answers.
So I'm going to kind of combine a couple of questions into one here that we received. So my role for CSU is I'm in charge of safety and security of biological research. So from my perspective, how do I find out that people like Jean are doing what they are doing unless they fill out a protocol for institutional review? So one, how do I find out like what he would do if what he's doing, or some rogue grad student is doing if there is no protocol associated with it? Two, we have a lot of legacy equipment, for laboratories, high containment laboratories, normal laboratories. Here at CSU, we have a regional biocontainment lab. We have Biomark, which is a vaccine manufacturing, organization. What can we do to deal with some of that legacy piece of equipment? What can we do to help protect ourselves? Because a lot of what we're talking about requires large dollar amounts. From a cyber biosecurity perspective, you need a lot of money to keep up with these things. So what can institutions do to help protect their bioeconomy and to prevent from much larger types of attacks?
I'm going to pitch in there. So I think that, one of the vulnerabilities of, that we are dealing with is that all our biosafety and to some extent our biosecurity policies are essentially based on self-disclosure, voluntary self-disclosure. And there is just no, if I want you to help me, you will be there. But if I want to work without you, it's kind of difficult to figure out what's going on in my lab. And this is, this is not just you, it's also me and my students and that kind of thing. So I think that there is just, it's not necessary, it doesn't necessarily take a bad actor for something bad to happen. It's just, miscommunication or sloppiness or, things like this. So having, trying to get information a little bit more systematically would help increase our awareness of what's going on in our labs. And the more people are looking at it, the better, the safer we are. It's good that you're looking at it. I should have a way of knowing what my students are doing. I don't, and things like this. So, paradoxically, I think that's where software could actually be useful. It's kind of a double-edged sword, because everything that you put on software, becomes vulnerable to more attacks. But you can make software secure, and maybe that, secure information in software, like, having a LIMS systems for a large organization, having like IT policies around biological data, biological process, and things like this could go a long way. You can make that robust if you put a lot of effort into it. But there's a lot of things that, if you just ignore it, it's going to come back to haunt you. And not having that information is the worst position in terms of managing the risk.
Yeah, I'd focus on three pieces of short advice. First, understand those elements of your biological process or lab that are of highest consequence to you, and focus on those first, right? Because there's a lot to concentrate on. You don't want to get distracted with things that are of less consequence and maybe under less control. The second thing is that as the process expert, you have an advantage. No one knows the process or your laboratory or the data that you're gathering or the sequence or the purpose of it more than you. And so use that to your advantage when thinking about how you want to manage or mitigate risks for these high consequence events. And there'll be hopefully some other technologies and twinning concepts and other things that will come down the road that will help you relate that. The third piece of advice I have is just this curiosity and sort of pressure that you apply to your vendors in conversations. If you're having a conversation with a vendor and they don't have an upgrade path for their Windows operating system to something more modern or they're not embracing modern software practices, and they're part of the problem. Doesn't mean that you can move away from them immediately, but if you don't have the conversations, part of what we did on the power grid was we wrote some guidelines on how you put it in your contracts. And here's legally what you're trying to achieve. Here's technically what you're trying to achieve. And here's how you explain it to your manager as to why it's in the contract. And when you do that, you change as a community the procurement practices, and then it becomes a vendor expectation so that some of the hygiene issues are taken off the table so you can concentrate on what's more important.
A critical aspect, I'm going to bounce back a little bit to the question that was asked also before, but a critical aspect is actually the economics of security. I mean, security always seems like wasted money until after you've been hit. So, what is the upside of being more secure? And I think that, in the life sciences, there is a lot of documented evidence that we have reproducibility issues. The community as a whole works with crappy data. The efficiency of the research and development processes is fairly dismal, has been decreasing. And I think that the upside of more security and paying more attention to that would actually lead to more increased productivity. And you don't need to wait to be hit by a bad guy or ever a negative incident. I think that if we put our house in order by, paying more attention to the security of our data, the quality, that will translate into higher quality, more reproducibility, and more successful projects. So I think that we should be able to get our money back if we put some investment in this.
Yeah. So that begs the question, though: how do we go about changing the culture? Wayne talked a little bit about how to put pressure on vendors and kind of change the software side of culture. But what can we do to change the culture of other critical pieces of infrastructure from an institute, like from an academic research institution all the way to a power company? Because a lot of, again, has to do with that. And that's something we talk about in many different fields. And it's a very difficult thing to do, how to change that culture.
Yeah, I think Jean was totally right. I mean, it's difficult to make that prospective ROI sort of stick. I mean, clearly we don't do it in this sector yet, and we don't do it in other sectors either, right? So we've made that mistake in other environments before. So I guess I have to wonder aloud if an incident has to happen before we really care, and what will happen, and whether people pay attention, when that happens. I think it's just a matter of time. But we need to be very vigilant and understand that this is a need, and make it very clear what the case is. I mean, how much money are you losing? I mean, I think you go back to the private sector. How much money are you losing? If it's a nebulous ROI, nobody's going to actually pay for it. But if all of a sudden your power plant is off for 3 days, well, you sure as heck are going to start investing in it. So I think that's part of the culture. I think recognizing that this truly is not just in meetings like this critical infrastructure, but really recognizing it officially is essential, because otherwise it's just, I mean, same thing with the power grid, right? I mean, see, the drive to push DHS CISA to actually identify a number of sectors as critical were key enablers to actually focus the government and the private sector on actually recognizing this as a problem. So I think we need to do the same for our field.
Now, the Department of Defense has, a cyber command. Are there any other analogous organizations within NIH, USDA, CDC that are kind of trying to do the same thing? Because we do have a NIST standard, and you're starting to see some grants here and there from an academic perspective that do require higher levels of cybersecurity to obtain the money and to handle the data. But we're not seeing that uniformly across the board.
Wayne, you want to take that one?
Well,
I'll throw you
on
under
the
the bus.
commercial side of the sector, although young and not declared a distinct sector itself, certainly based on the activity and the hacking activity and the threats that were going on through Operation Warp Speed and others, DHS and CISA has been engaging, been extending their sensor networks and other related items. From a cyber command standpoint, right, in the larger whole of government, cyber command will be brought to bear in a forward-leaning sense, when they see strategic risk, both from an economic standpoint and from a national security threat. So they're already part of it if they just recognize the uniqueness of this sector and some of the uniqueness of the consequences, right? What I find is that there's actually an over-richness of threat information, but what part of it is important requires the sector expertise to try to digest it. And so, 10 years ago, I would have conversations with the Intel committees or other folks about, they would say, we see this, is this important? We see this as important. Well, we don't have those conversations as much anymore because we went through that sense of prioritization, not just in a functional sense, but in a technology sense. We fuse those information streams through ISACs and other mechanisms so that you have experts that can tell, oh, this is really important. This is why this particular sequencer or this particular technology is important. And if it's on that actor's radar screen or they have this capability, these are the impacts. And so to me, these seminal processes that ended in Charles's presentation are sort of those starting points. What we can't do is take 10 years to build the momentum on them. We've done these in other sectors. This one's unique. It has some other, multidisciplinary challenges that we have to create, but we've done it and we're making momentum in those. We have the starting points. Let's build off of forums and ISACs like this and the manufacturing institutes, and we can accelerate impact here in years instead of decades like it took for the first couple sectors.
Yeah, and the government could have a leading role in this, especially NIH, because any policy or guidelines that NIH puts in place, and there is so much money at stake that everybody is going to change their ways. So, like for instance, it's very troubling that we are still all relying on a gene bank that is totally insecure. And this is a major vulnerability because anybody can submit any kind of data, any kind of misleading data, and that kind of things. And can we imagine all the bioinformatics resources provided by NIH? If the NIH could actually provide community resources that would be robust and secure and still accessible to the community, and then ask the people that they found to actually do a little bit more than what they are requested to do in their data management plans today. I mean, the entire community would flip because they want the NIH money. But if the NIH is sloppy, then why should we care?
So we've talked a lot about adversaries, people who are intending to do these types of things. What about in the event of an accident or a researcher that is just so excited they developed something so cool that they put it on an open access, page, and everybody's like, oh my gosh, that has got dual use potential, So how do we kind of prepare for things like that, either from a training perspective, a proactive communication perspective? What about those incidents of it not being a nefarious person or persons?
I'll take. So I think it comes down to culture. And here we have a phenomenal example. Again, I mean, Ed, you deserves all the credit that everybody gives him. I actually met Ed in a very different context because I was one of the sort of founders of the do-it-yourself biology movement in this country. And so I actually met Ed many years ago in that context. And it comes down to culture, the culture that Ed and others actually seeded in this environment. Phenomenal. Look at iGEM and look at the culture that came out of that around biosecurity. Well, we need to do the same. We need to understand how important the stakes are to our country, to our allies, and what we can contribute as a country to the rest of the world. This is to me, this is a very simple example of showing the importance of having a secure environment that we can contribute to the rest of the world. It's essential. That's part of the culture. We have to build defending as an essential part of the culture in digital biosecurity. And we can do it. Ed has done it before in the biosecurity space and synthetic biology space, and we can do the same in this space. All the actors are already gathered. We just need to make a conscious effort and concerted effort in that direction.
What can academic institutions such as CSU do to support that? I mean, I wholeheartedly agree with you. I am in this space and I know this space because of EDU. And, you know, talking to him over the years, sitting through the various talks, spending a lot of time learning to essentially think like a bad person. So what could CSU do to help train future generations of scientists? I mean, if you want, I can plug my own course right now, but that is only like a tiny little lecture in biosecurity about the importance of cybersecurity.
Give Rebecca 4 more courses.
4 more courses.
I sometimes think of it as an evolution between rallying the multidisciplinary teams and then interdisciplinary teams. And so the end state, when you truly have one of these new earth-shaking domains like bio manufacturing is, right? You're really creating not just multidisciplinary teams that are addressing the problem. You evolve to an interdisciplinary curriculum, if you will, in which you don't just learn about the sequencers, you learn about that ecosystem and tools and using not just bits and bytes encryption, but fundamental practices in which you use your knowledge of the biological processes as part of your natural defense, if you will, at all stages. And then you've evolved, you know, past what the average hacking threat actor, you know, has. And I think that's a market, that's a measurement, if you will, for success. So your coursework, to the degree that it starts evolving towards that, I think would be relevant. And I say that without actually looking at your syllabus. So
thanks. So we've got 3 minutes left. Do you guys want to leave us with any closing statements or things to ponder for the weekend? I know I certainly learned a lot from you. I didn't necessarily realize how compound things are now and how multi-step it is. And, you know, just from my perspective, learning that and understanding that and bringing that into my daily job is incredibly important.
yeah, I would just say, like many things, more thought in the beginning saves you later, right? And it may feel like that it's, you know, like many things, right? You know, that you've delayed yourself a little bit, but I think in the end, in the aggregate, both for the product and the larger economic and national security sense, a little bit more thought in the beginning about those, what can go wrong, what you know about the process that can be indicators of good behaviors and bad behaviors. That innate curiosity of how things can go wrong is so useful in the beginning, and I think shapes you through the whole process. And you do that in a diverse thought team, diverse product team, and I think that there will be lots of goodness from that with minimal investment.
It seems to me that we should not underestimate the value of the conversation that we're having here. I mean, that's the first step toward the change of culture, the fact that there is an awareness, that there is a community of interest, that people are talking about it. I mean, you know, 5 years ago, a much smaller community of people were worried. So you know, we may not have all figured it out, but we are certainly making some steps in the right directions.
Yeah, I'll just leave by saying, echoing Jean's comments here. You have to really realize how big this is. It really is. Biology is possibly the, you know, fourth and final cardinal science to undergo this technological transformation, and we're in the midst of it. I mean, if we haven't passed the inflection point yet, we're very close. We will see it in our lifetimes, and that means a seismic change in terms of everyday life and technology availability on the biological side, right? Everything from performance materials, to, life-saving medicines that a good portion of us here in the US have gotten, for example, the Moderna vaccine being one of them, sort of mRNA vaccines. This is only going to get in accelerating, and it's going to get faster and faster and faster. And so for us to take stock of how shoddy the foundation is now and get really busy both in the private and public sectors in shoring that up today is going to yield exponential sort of robustness for the years to come. And time is running out pretty darn fast here. So yeah, if you're in the early parts of your career, please, or even later, just start looking. Please come with pick and shovel ready, because we have a ton of work for you, like in the private sector and the public sector. And we're now building these vehicles so that you can very directly contribute to things that are life-saving and absolutely essential for our country and the species as a whole. So, it's fulfilling work, but it's a lot of work.
I think that's a good way to end this session. Well put, Charles. Jean, Wayne, Charles, thank you so much for your time. This was a fascinating conversation. I believe I'm supposed to turn it over to Meg now.
Rebecca, panelists, thank you for this robust discussion as a part of our second session. Really powerful comments by all of you. As noted in the agenda, we will be transitioning to a short break until 3:40 p.m. Mountain Time, and we invite you all to rejoin us at that time for our final session.